Hi everyone, our next experiment will be amide synthesis. In this experiment, we're going to be identify an unknown amine. This is the third or fourth multi-outcome experiment that we did this semester, right? Back before, you had a candidate bank to choose from for the identification. Starting from this experiment, you're not going to be given a candidate bank, so that you cannot rule the wrong answers out, right? You have to use your own spectral analysis skills to identify the unknown. This experiment, we're going to use FTIR, proton NMR, and melting point determination for the calculation of the product. Think about it, and if I were you, I would analyze, or I would gather as much information as possible from all three characteristics method, so that I can gather all the information I need for the identification of unknown. Okay. Alright, so there are several ways you can synthesize an amide. The first one being you start with a carboxylic acid and a amine using some kind of coupling reagent. DCC was one of the common ones we use. DCU will be a byproduct of DCC. This reaction sometimes goes sluggishly. If you go into peptide chemistry or protein chemistry in the future, then you may encounter a lot of similar reactions. Sometimes, if you have a very bulky starting reagent, the reaction may go sluggishly. It may take even overnight or 3 or 4 hours. And sometimes the reaction will go pretty fast with only 1 hour or 30 minutes. So it depends on what kind of coupling reagent you use and what is the starting material to say how fast the reaction takes. Second reaction is hydrolysis of a nitrile. The third reaction is the one we use today, which is that we start with a acetic anhydride to react with an amine to form an amide. You may either use catalysts or not. There are several different catalysts you may choose from. Aluminum oxide was the one we chose for today's reaction, but some other catalysts were also available for the reaction. If you do not use any catalyst, the reaction will go very sluggishly. Sometimes it will take overnight for it to complete. The fourth method is going to be we start with an acyl chloride to react with an amine. As we know, acyl chloride is very reactive. It will react with a range of starting materials to form a bunch of final products. It also means that the reaction sometimes will go very violently, and it may lead to byproduct. The reason we're not going to be using acyl chloride is because it's so reactive that it's very hard to control the outcome. So we chose the third one, the third method to synthesize an amide. The mechanism follows 3 main steps. First one being nucleophilic attack of the amine onto the carbonyl group in the acetic anhydride. The reaction will lead to the formation of an alkoxide, and the second step will be deprotonation by the amine. The very last step will be restore carbonyl group and form the amide bond. At the same time, the acetate group will be leaving as a leaving group. The reaction goes pretty smoothly. There's 2 things I want to emphasize for the mechanism. Firstly, the reaction goes in a stepwise manner. Sometimes I see students combining all the arrows onto the same product. However, that's not what happened, right? Because all the arrow pushing, all the electron donating, or the electron transfer do not happen at the same time. Also, if you combine all the arrows onto the same compound, you do not show the presence of the intermediate, right? So that was wrong. secondly, it follows an order, right? Which one happened first? Is that the leaving group or the deprotonation? Make sure that you're following the right order when writing a mechanism. I do not require students to include the byproduct, so you can either have it or not have it, okay? And be very careful about the cations and the anions. Where will the charge be attached to, okay? Thirdly, I want to explain why we use aluminum oxide. There are two main reasons. Firstly, aluminum oxide was very polar. It's also slightly basic. So it's going to provide both a polar surface for the reaction to proceed, which is a kind of an advantage for the nucleophilic attack to happen. Secondly, you're producing an acetic acid as a byproduct. Aluminum oxide, being a base, can react with the acetic acid byproduct, which is also a good sign for your reaction. And what I'm showing you up here is a balanced equation, which means that you need to put all the starting material on the left, all the final product, including the byproduct on the right of the arrow. If you have a catalyst, it will sit on top of the arrow. If the reaction requires heating, microwave, reflux, those also need to be included on top or at the bottom of the arrow, okay? Right. And last but not the least, safety. Firstly, the reaction was exothermic. And you will see what I mean when you're running the reaction yourself. You can hear the popping sound. You can sometimes see the liquid jumping around and splash around. So be very careful when you're adding your reagent in a drop-wise manner, okay? If the reaction goes very violently, slow down the addition of the reagent, okay? And you may also swirl the flask after the addition of the product, because sometimes the reacting reagent will be splashed onto the walls of the flask. So in the end, they do not even participate in the reaction. All those starting material will be the impurity in your final product, which will show up in the proton NMR and in the FTIR. Okay, so make sure that you swirl the flask. All the liquid will be mixed up evenly to ensure the reaction goes to completion. That's the first thing. Second thing is that make sure you use a snorkel. Almost all the amine will have a very foul smell. You will know exactly what I mean when you walk into the lab next week. So it's volatile, it have a distinctive smell, and please use snorkel. It's also potentially toxic to your body, okay? Thirdly, we're going to use ethyl acetate as the extraction solvent. First question, is that going to be on the top layer or at the bottom layer? That will depend on the density of ethyl acetate, right? However, if you go into the details, you will realize that we're going to start with acetic anhydride, which is a liquid, and a primary amine, which is also going to be a liquid, to form a solid product in aluminum oxide catalyst, right? Which means that when you're extracting your solid product into ethyl acetate, it's going to be a liquid solid extraction. The compound that's going to be left onto the filter paper on the funnel will be unreacted catalyst aluminum oxide, which means that there won't be any aqueous layer, right? So you don't have to worry about the density of ethyl acetate. And always follow your product, which is a solid being extracted and dissolved into ethyl acetate. So follow the liquid filtrate. And then you will be worried about the boiling point of ethyl acetate, right? Because you need to get rid of all the ethyl acetate and form the final solid product. So please look up the boiling point and then add 20 degrees above that number when you're evaporating off the extraction solvent. You're also going to see your solid product being formed on your beaker during the evaporation. How can I describe this? So the product you're going to be forming may have a lower boiling point, it may have a lower melting point compared to the boiling point of ethyl acetate, which means that it will remain in a liquid form on the hot plate, although all the ethyl acetate evaporated off. So if I were you, when you have like very minimum amount of liquid left, you can take it off from the hot plate every now and then to see if it's solidified or not. If it's solidified, then you don't have any ethyl acetate. You're going to see the product being formed at the bottom of the beaker when the temperature cools down. If it still remains in the liquid form, then you know you still have some ethyl acetate. Make sure to put that back on and get rid of all the solvent. Does that make sense? You're going to know what I'm referring to when you're running the reaction yourself, right? Because sometimes students will be asking, I've been boiling off my solvent for an hour. How come I still have only liquid? That's because your product melted on the hot plate. You may have the temperature to cool down for the solid to be formed. Okay. That's everything I can think of for this experiment. The procedure wasn't so complicated. We've done almost all of those techniques in the previous experiment, which left us the hard part, which is the spectral analysis and identification of unknown. Okay. Again, if you have any questions, either drop by my office at Chemistry 452 or schedule an appointment so we can talk through Zoom or schedule an in-person meeting. Okay, I'll see you next Tuesday.